I'm going to cover a few examples of when and how to use L'Hopital's rules when you're taking the limits of x as they go to 0 or infinity or whichever number they go to. So start off with this basic example on number 1. So we have the limit as x goes to 3. We have x minus 3 over x squared minus 9. If we do take the limit, you have 3 minus 3, which is 0. You got x squared minus 9, so that's 3 squared minus 9. That's 9 minus 9 is also 0. So we gotta basically fix this in order to take the limit. So if we rewrite this equation, look at this bottom right here. X squared minus 9, that's a difference of 2 squares. This is basically x plus 3 times x minus 3. So we just simplified it, all right? We just kind of like reverse foiled it. If we see here, the numerator and the denominator cancel out. So you just get 1 over x plus 3, right? So basically, the limit as x goes to 3 of x minus 3 over x squared minus 9 is equal to 1 over the x value that we want, 3 plus 3, which is 1 over 6. That's our answer for that one. So that didn't need the use of L'Hopital's rules. But sometimes we need L'Hopital's rules when we do stuff like this. So you have tangent of 3x over sine of 2x. So if we plug in 0 for tan of 3x, that's tangent of 0, and that gives us 0. So this is 0 here. And if we have sine of 2x, and this is if sine, and then we get sine of 0 if we plug in 0, that's also 0. So we have to figure this stuff out. Now we can't just factor this stuff out, or can we? So let's try that out. So we have tangent of 3x is equal to sine of 3x over cosine of 3x. Now the issue is divided by sine of 2x. We can't really simplify this. So we tried simplifying it, it doesn't work. So let's try using L'Hopital's rules. So if we use L'Hopital's rule, we're just going to take the derivative of the numerator and the derivative of the denominator separately. We're not using quotient rules here. We're just going to take the derivative of the top and the bottom separately, and then we're going to compare them. So if we do that, we get the limit as x goes to 0, right? The derivative of the top, the derivative of tangent, is secant squared. And then we have chain rule here, so we have to multiply the outside by 3. So we get 3 times secant squared of 3x. If you didn't see that, basically you took the derivative of tangent of 3x, we get secant squared of 3x, multiply that by derivative of the inside, which is 3x, and you get 3. Over, and then we'll do the same thing for sine, which gives us 2 cosine of 2x. We can actually simplify this even more. This equation right here, if we separate it, 2 cosine of 2x, what we do know of secant squared is that secant x, right, is just equal to 1 over cosine of x. So we can write it that way. So we can basically, this is multiplied by 1 over, and then we'll keep the 3 on the top because that doesn't move. That's basically 3 over cosine squared of 3x, right? Now we can take our limit. So if we look, cosine of 0, if we plug in 0 here for 2 cosine of 2x, we get cosine of 0, correct? And cosine of 0 is just equal to 1. So this whole thing is equal to 2. And then this part, same thing. Cosine squared of 0 is just basically cosine squared of, or it's just 1 squared, essentially. So you get 1 over here, right? So we have 3 divided by 2 times 1, which is 3 halves. So if we take the limit here, the limit as x goes to 0 of this equation right here, tangent of 3x over sine of 2x, is just equal to 3 halves. That's basically our equation there, right? That's one example of using basically trigonometric identities in order to solve it. Now, the last example here is x squared times natural log of x. Now, the thing is, we don't see any denominators here. If we plug in x to 0, we have a 0, right? And then we plug in 0 for natural log of x, we get a negative infinity. If you look at the natural log equation, as x approaches 0, we get a negative infinity. So you have a 0 times a negative infinity. This doesn't work. And so we need to figure out. Now, we don't have a denominator, like I said, in order to do L'Hopital's rule. So we have to rearrange this somehow. So isn't this true that this is equal to x squared times natural log of x? And if we have this over 1, we'll do that, right? So we can also write this as natural log of x divided by 1 over x squared, right? Because when we divide by 1 over x squared, we're multiplying by x squared. These two are equivalent. We can do that. Now we have a numerator and now we have a denominator. And so we can take derivatives. So let's do that. So the limit, as x goes to 0, of the derivative of the top. So when we take the derivative of natural log of x, we get 1 over x. So we get 1 over x over, and the derivative of 1 over x squared, which is equal to x to the negative 2, we get negative 2, basically x to the negative 3. So this will be negative 2 over x cubed, essentially. Now we can simplify this. This is equal to 1 over x multiplied by x cubed over negative 2. If we cancel out the x, cancel out this becomes squared. We got x squared over negative 2. So basically, now we can plug in our 0, right? So if we plug in 0 here, we get a 0, and that's just divided by negative 2. So now we can do that. So that our answer here is just 0. So we finished it. Now we just have to write that the limit as x goes to 0 of x squared times the natural log of x is just equal to 0. And those are 3 different examples of how to use L'Hopital's rules. So, and then the first example, like we mentioned, sometimes you don't need to if you can simplify it.